This is Lesson 10, the first of 3 lessons, 10, 11, and 12, that will cover the solution of systems of linear equations. What I'd first like to do is discuss the rationale for learning systems of linear equations and also maybe figure out what they are, and then go into 2 of the types of solutions, have you do a problem that uses both types of solutions, and if we have time, then discuss a 3rd type of solution. A system of equations is simply more than one equation, and when we solve it, we're generally looking for the intersection, where the equations intersect. Whatever that means, we'll see as we look at the first visual. The first visual is my version of something called the Malthusian doctrine. And for those of you who are history buffs, or if you show this to your history teacher, they'll say he's wrong. I understand. I'm just taking what Malthus said. Malthus was an economist and an Anglican preacher who lived in England, who discussed the relationship between the population and the supply and demand of food back, about 200 years ago. And the graph shows my interpretation of what he was saying. The blue graph is the demand for food. The blue graph, the blue line, labeled D, is based on population. Notice the x-axis is the year, the y-axis is food. The white line, which has an S, is the supply of food. And the intersection of those 2 lines is quite important. Why is it important? Because where they intersect, the demand and supply of food will be identical. Beyond that year, the supply of food will be less than, it's below the demand for food, and therefore there will be famine. Of course, as it turns out, Malthus was incorrect. There are a lot of reasons for that. You can consult your history books. But the fact is, he was dealing with a system of 2 linear equations. That is, 2 lines, one which represented demand, one which represented supply. He was concerned about the intersection. Let's talk about intersection for a moment. If you are standing at the intersection of Main Street and Broadway, what does that mean? Well, first of all, hopefully you're not standing there because you're probably getting run down by a car. But if you were, if there were no cars present, and you were standing at the intersection of Main Street and Broadway, it would mean you were standing at Main Street, actually in Main Street, and also simultaneously standing in Broadway. You were in both streets. The intersection point for 2 lines is where the 2 lines cross, and that point, the XY ordered pair, would be the only ordered pair that would work in both of the equations, the only ordered pair that would be on both lines. Now, what we're going to do is we're going to take 2 linear equations and find out how we can solve them. For example, let's go to the board here and look at these 2 linear equations. Y equals 3x minus 4 and y equals 2x plus 1. We're concerned about here is where those 2 lines cross, the value of x and y that will work in both equations. And we're going to first attempt to solve this system of equations by graphing. So let's look at the next visual. And the next visual shows us those 2 equations and the graphs of the 2 lines. Which line do you think is y equals 3x minus 4? Is it the red line or the blue line? You should have said the red line. The reason is very simple. The red line has a steeper slope. Notice that y equals 3x minus 4 has a slope of 3, while y equals 2x plus 1 has a slope of 2. Also, the red line has a y-intercept below the x-axis. And of course, the intercept for y equals 3x minus 4 is negative 4. But the important point here is where the 2 lines intersect. They intersect at the point 5, 11. X equals 5 and y equals 11, which means that 5 for x and 11 for y is the only ordered pair that will work in both equations. As always, we're going to check. And we check by plugging in 5, 11 for x and y into both equations, which is seen on the next visual. And that visual shows us that we plug in 5 for x and 11 for y, and 11 equals 15 minus 4. That checks. And then we plug in 5 and 11 for x and y equals 2x plus 1. 11 equals 2 times 5 plus 1. That also checks. We must check in both equations. And indeed, we have now found that the point x equals 5, y equals 11 is the only solution to our two equations. We have solved the system of equations graphically. Okay, let's take a look at the next visual. The next visual has a real problem to it. Y equals 2x plus 3, and 3x minus 5y equals negative 1. What kind of problem might that be? Well, if you look at that second equation, if you got to get that second equation into y equals mx plus b, the slope is going to be a fraction. As I mentioned in earlier lessons, I don't like fractions. You might not like fractions, and graphing fractional slopes sometimes gets really confusing and leads to errors. So we need to find a better way to do that. And the way, other than graphing, to solve systems of linear equations is a method called substitution. Notice that the first equation in our visual is y equals 2x plus 3. We have y directly in terms of x. And therefore, as seen in the visual, we can exchange the y in the second equation and make it into 2x plus 3. Since y equals 2x plus 3, we can replace the y with 2x plus 3. Just as if I gave you two $5 bills for a 10, that's fine. The two 5s would replace the 10. It's a valid substitution. So on the third line on our visual, we see 3x minus 5, parentheses, 2x plus 3, close parentheses, equals negative 1. We've taken the second equation and replaced the y with 2x plus 3. Now we're back to where we were early on in this series of lessons. We're solving an equation with parentheses. We multiply through, combine like terms, and divided by the coefficient negative 7 to get x equals negative 2. My obvious question now is, what are we going to do when we solve x equals negative 2? Some of you may say it's time to check, and you would not be quite right. Because remember, when we're solving a system of equations, we're solving for an intersection point. And that point has both an x value and a y value. We cannot check until we got a complete solution. A complete solution here would be x and y. So, let's look at the, let's not look. Let's take a look at what we need to do first. And what do we need to do? We need to plug in the solution, which is x equals negative 2, into our original equation y equals 2x plus 3. Okay? And now we can go ahead and look at that visual to see how we do that. And it's really quite simple. We've simply replaced the 2 with negative 2 and solved for y. We get negative 1. And the last line on the visual shows us the ordered pair negative 2, comma, negative 1. X equals negative 2, y equals negative 1. Now that we have a solution, now it's time to check. And we're going to check by replacing the x and the y with negative 2 for x and negative 1 in both equations. I must emphasize, we must check in both equations. The next visual shows us that. We've replaced the 3x minus 5y equals negative 1. That is the one of the original equations. We replaced the 3x minus 5y equals negative 1 with x equals negative 2 and y equals negative 1. And 3 times negative 2, negative 6 plus 5 is negative 1. That checks. Now the question is, I said checking in both equations. We could go back to the equation y equals 2x plus 3 and check that. But indeed, since we used that equation to solve for the y, the negative 1, when we had x, there really is no need to check. If you want to, you can do that, and you could check in both equations. But since we used the original equation, y equals 2x plus 3, to solve for y when we knew x was negative 2, there's no need to check in that one. We must check in the other original equation. And as we saw on the visual, it did check, so we know that negative 2, negative 1 is the only ordered pair, the only value of x and y that works in both equations. There are many, many values of x and y that will work in one equation, but they will not work in the other equation. This is the only ordered pair that works in both. It is indeed the intersection, and therefore is the solution to our system of equations. Let's take a look at a second substitution problem. In fact, let's go ahead and look at the next visual. The next visual gives us this problem. 2x plus 4y equals 2, and 5x minus 2y equals 17. Now, what's different about this problem? What's different is we don't have one of the two problems written as y equals a function of x or x equals a function of y. To do substitution, to use the method of substitution to solve a system of linear equations, we must be able to get one of the equations to form x equals a function of y or y equals a function of x. So notice the arrow shows you in this visual that we've taken 2x plus 4y equals 2 and written it as 2x equals negative 4y plus 2 by subtracting 4y from both sides, divided everything by 2 and getting x equals negative 2y plus 1. We now have x in terms of y. This method is called substitution because what we're going to do is substitute that function of y for the x in the other equation being 5x minus 2y equals 17. So if we look at the next visual, we'll see that we replace the x with parentheses negative 2y plus 1 because we just saw that that was what x was equal to. And now we have an equation with one variable, one letter, y, and we've multiplied through the parentheses, combine like terms, we get negative 12y equals 12. Dividing by negative 12, we get y equals negative 1, which is the solution for y. We have not yet gotten the solution for the system because we need to get the value of the other letter, in this case, x. The next visual shows us how to do that. X equals negative 2y plus 1. That was something we found out, and therefore we replace the y with negative 1, and x must equal 3. Thus, our ordered pair is 3, negative 1. That's the solution. X is 3, y is negative 1. Now we need to check. I want you to remember something I said. In the previous problem, I only checked in the one equation because the other equation, we used the original equation to obtain one letter given the other. Here, remember, we did not do that. We modified one equation to get it in the form x equals. So now we must check in both equations. The next visual will show that. Here's the check. 2x plus 4y equals 2 was the equation we played around with to get x as a function of y. We go back to the original equation, replace the x with 3, the y with negative 1, 6 plus a negative 4 equals 2. That checks. Then we go to the second equation, 5x minus 2y equals 17. We replace the x with 3, the y with negative 1, and 15 plus 2 equals 17. The answer, 3, negative 1, checked in both equations. It is correct, and we know we have the right answer to this system. What I'd like to do now is to do another problem. But before I do it, I want you to do it. So what I'd like to do is I'd like to look at the next visual. The next visual shows us 2x minus 3y equals 9, and x plus y equals 7. Write those two equations down. And what I'd like you to do is, after I'm finished babbling here, is to stop the tape and work the equations using both methods. Work the equations by graphing, work the equations by substitution, and check, and of course both answers should be the same. When you turn back onto the tape, I will certainly go through those two methods, and it's silly for you to proceed until you've actually done it because we can check and make sure you know how to use both methods. So at this time, go ahead and turn off the tape. Now, if you just turn back on the tape, you should have worked, or at least attempted, both solutions. Let's take a look at the graphical solution to our system of equations. The next visual shows us the graph of those two equations. Notice that before we can graph the equations, we need to convert them to y equals mx plus b form. And indeed we have done that. The 2x minus 3y equals 9 becomes y equals 2/3 x minus 3. The x plus y equals 7 becomes y equals negative x plus 7. We graph the two lines, and again, you can use any method you like to graph. The slope-intercept method, plotting points, the x-intercept, y-intercept method. We have the two lines. They intersect, apparently, at x equals 6, y equals 1, as shown on the visual. So we now have our solution, and we have the solution graphically. And we should check that. Let's go back and look. Let's write those two equations down on the board here. Let me erase these old equations and go on the board and see about checking them. Let's see. We have 2x minus 3y equals 9. And our second equation is x plus y equals 7. Notice that I am not using the equations in mx plus b form. I'm going back, as always, to the original equations. And now we said the solution is 6, 1. So I'm going to replace the x with 6. 2 times 6 is 12. And the y with 1. 3 times 1 is 3. And indeed, 12 minus 3 equals 9. X is 6. Y is 1. And indeed, 6 plus 1 is 7. So we've seen that indeed the solution to these two equations, the system of equations we show here, is indeed x equals 6, y equals 1. But remember, I asked you to do this in two ways. The second way was using substitution. So let's look at the next visual and see how we did that. In this visual, we can see that we took the equation x plus y equals 7 and solved it for x. X equals 7 minus y. We replaced the x in the other equation, 2x minus 3y equals 9, with 7 minus y. And we get the equation as seen on the second line, 2, parentheses, 7 minus y, close parentheses, minus 3y equals 9. And once again, you can see the importance of solving equations, because we now combine like terms. We get negative 5y equals negative 5, divide by negative 5, and get y equals 1. On the last line, we go back to the other equation, the x equals 7 minus y, replace the y with 1, and we get negative 1, which of course is with 7 minus y, and minus 1 plus 7 equals 6. So we again get x equals 6 and y equals negative 1. Sorry, y equals 1. So that's x equals 6 and y equals 1. And our check would be the same as it is here. Again, even though we used a different method, the method of substitution rather than graphing, if our solution was 6, 1, and these were our two original equations, our check would be the same. And as we've seen, indeed it does check. So let's talk momentarily about the two methods we've used, and then it looks like we'll have some time. We'll go on and look at a third method, which is called solving by addition of equations, and we'll proceed with that, which will lead right into Lesson 11, which will take up some more complex types of equations. What we've done so far is looking at the solution to two equations to find the intersection point. The first method was graphing. Get the equations in some form, probably y equals mx plus b, that you can graph the two equations on the same set of axes, and where the two lines cross, that's your solution. Find the x and y, go back, plug the x and y into the original equations, and check that that solution is indeed working for both solutions. The second method we used was by substitution. We either had one equation that had x equals a function of y, or possibly y equals a function of x. If we didn't have that, we took one of the equations and solved it for x. So we got x equals a function of y, or we solved it for y. We got y equals a function of x. And then we substituted, so we got an equation with only one variable. We know how to solve those. We solved. We used the other equation to find the value of the second letter, and then we went back and checked in the two original equations. Quite frankly, those work well, but they're not the easiest methods to use. As we saw with the graphing, we could wind up with some fractional situations. In substitution, we have a problem. Sometimes it's not very easy to take either of the equations and get x as a function of y or y as a function of x without running into problems with fractions. And again, you may enjoy fractions, I don't. Historically, many of my students have great problems with solving equations that have fractional numbers. If we can avoid that, that sounds very good. And the way to avoid that is by looking at adding equations. Now you say, well, what do you mean adding equations? Well, if we have two equations, let's take an example. Let's go to the board again here. And let's take an equation like 2x plus 3y equals 8. And how about 5x minus 2y equals 1? If I added those two equations up, what would it do? Would it create another equation? Can you prove that? If you said the answer was yes or no. And the answer, by the way, is yes. And the way to prove it is, hey, 2x plus 3y, that equals 8. If I add 5x minus 2y to this, it's no different than adding 1 to the 8. I'm adding equals and equals. What I get is an equation. In this case, remembering from Algebra 1, we can only add x's and x's. 2x plus 5x is 7x. Positive 3y and a negative 2y is plus y. And 8 plus 1 is 9. And you might say to us right now, well, what good have we done? We haven't done any good in terms of solution. I was doing this to show you how we could add equations. Our goal in adding equations, you see, is to eliminate one of the letters. We can do that by eliminating the x's. For example, if this had been 2x and this had been negative 2x, when we added those equations up, the x's would go away. If this had been a positive 3y and a negative 3y, the y's would have gone away. So we either eliminate the x's or eliminate the y's. How would we do that here? We'll leave that for lesson 11. But right now, we want to look at equations that are in such form that if we do add the two equations up, we can immediately eliminate one of the letters and go ahead and solve. Because remember, once we get down to an equation with only one letter in it, we know how to solve those. So let's take a look at the first visual in this problem. And the first visual gives us the two equations. 2x minus 3y equals negative 13, and 5x plus 3y equals negative 1. Notice it would not be very interesting to graph these two equations, because you get it in slope-intercept form. You would have a slope of 2/3, which is and plus a y-intercept of 13/3, which is not a very interesting y-intercept to plot. That's for the first graph. And the second line would have a slope of negative 5/3 and a y-intercept of negative 1/3. We could use substitution, but again, in solving either of these equations for x or y, we'd wind up with fractional values. And it really would be a problem working with those. But notice something very, very nice. In the first equation, the one on top, we have a negative 3y. In the bottom equation, we have a positive 3y. If we should add those two equations up, the y's would go bye-bye, as we say. They would disappear. They would cancel each other out because they have the same number with opposite signs. And indeed, that's exactly what we do in the next visual. We add the two equations up. 2x plus 5x is 7x. The negative 3y and the positive 3y is 0. And negative 13 and negative 1 is negative 14. Once we have an equation with only one variable in it, we have no problem solving it. And of course, here we simply divide by 7, and x equals negative 2. Are we done? Absolutely not. Remember, our solution has to have both an x and a y. So what do? We go back to one of the original equations. Let's look at the next visual. We can see I've selected to use 2x minus 3y equals negative 13. It doesn't make a difference which one you choose. We plug in the x of negative 2. So 2 times negative 2 minus 3y equals negative 13. And the rest of that lays out the solution. Again, we're back to one equation, one letter, in this case y. We can solve it. We add 4 to both sides. We get negative 3y equals negative 9. We divide by negative 3, y equals 3. And thus the last item in that visual is the solution, the ordered pair, negative 2, 3. Again, this means that for our two equations, 2x minus 3y equals negative 13, and 5x plus 3y equals negative 1, the only value of x and y that's common to both equations, the intersection point, is when x is negative 2 and y is 3. Now, we still need to check this, don't we? So let's look at the last visual in this set. And what we've done here is we've simply replaced the x and the y in the second equation, 5x plus 3y equals negative 1, with negative 2 and 3. The x is negative 2, the y is 3. We get negative 10 plus 9 equals negative 1. And that, of course, is correct. Why do we only check in one equation? Why didn't we check in the first equation, the 2x minus 3y equals negative 13? Because you'll remember, that's the equation I used to solve for y when we knew x. If you wanted to check in that equation, that's very fine. You can do it. But basically, you must check in the equation that you didn't use once you found the one letter. Could we have solved these equations by eliminating the y's? Well, obviously not. We did eliminate the y's. Could we have solved this equation, system of equations, by eliminating the x's? And the answer is not as we know right now, because as we saw, 2x plus 5x is 7x. It doesn't eliminate the x. The next thing we're going to do in the next lesson is to see if for some strange reason you had said, gee whiz, I don't want to eliminate the y's, I want to eliminate the x's. Or if the two equations were not of the type where you had an x in one that was a positive 4 and the x in the other was a negative 4, and you couldn't eliminate by adding. You know, for example, if we go back to the board here, remember this. What if we were faced with this particular set of equations? We certainly could not accomplish elimination by adding. We wouldn't want to get involved with graphing because of fractions. The same thing with substitution. And we'll talk about this next time. But right now, we do have 3 methods that are quite valid. We have the method of graphing, which is very, very good as long as you can easily graph the two lines. We have the method of substitution, which is an excellent way to work the solution if one of the two equations can be put in y as a function of x form or x as a function of y form. And then we have the addition method, which is simply very useful and exceptionally easy if either the two x's or the two y's have the same coefficient with opposite signs. As we saw here, we had the y's. One was negative 3y, the other was positive 3y. But ultimately, everything we've done in this lesson was to enable us to solve a system of two equations. Just as Malthus wanted to know where the supply and demand for food, those two lines would cross, in what year would the food and the demand for food and the supply of food be the same. Just as the business person running a company wants to know his or her break-even point, where revenue, the money coming in, would be the same as the cost or expense, the money he or she is expending. In those cases, we are dealing with systems of equations. Like I say, in the next lesson, we're going to deal with more complex equations, like the one we had on the board, and find a method that will work in every single case. And eventually, we're going to jump to a higher level. We're going to find out how we can solve systems of 3 equations with 3 letters. But that's for a later time. We'll see you in Lesson 11.